Uh, Good morning to everyone and those who are in the here in the room 141 at the Faculty of Civil Engineering, University of Belgrade, as well as the online audience. Thank you very much for attending this event. My name is Svetlana Brzev, and I'm president of the Serbian Association of Earthquake Engineering. Today we have a very interesting and important, going to discuss a very important topic, and that is seismic assessment of unreinforced masonry buildings, and share some experience about methodologies and application of those methodologies from New Zealand and Serbia. So the event will be about 3 hours, but before that, I just like to say a few words about, just to mention, Serbian Association of Earthquake Engineering was established in 2018 as a non-governmental, non-profit organization in Belgrade, Serbia. And our main objective is to raise awareness and to raise the level of practice of earthquake engineering in the country and other countries as well, if they're interested. We are governed by the board of directors, and we currently have close to 250 members from Serbia and neighboring countries. And we are a member of the International Association of Earthquake Engineering since our inception in 2018. So events like this are our main activity, in addition to newsletters and a few other activities. This time is a longer, normally we have lectures with one person, one presenter, but today we have several speakers. And coming to that, I'd like to, just a moment. To show the program, to share the program of today's event. I'm just giving a few introductory remarks and we'll say a few words about the topic. And then we have our guest speaker from from abroad, from far away country, New Zealand. And that is Jitendra Bothara, who is going to talk about experience from New Zealand. And after coffee break, so we'll have a half an hour coffee break from 10 to 10:30. So after Jitendra's talk and discussion. After the break, we have a few presentations that are related to ADRISEISMIC project, which was project where in which several countries in the region of Adriatic and Ionian Sea participated, including Serbia. And we have speakers talking about different aspects of the project. We will introduce those speakers after the break. So the idea is that from 10:30 to about, I would say, 11:45, there will be presentations. Questions could be asked after presentations, but we have 15 minutes time for discussion also at the end. And the event will definitely end at 12 noon. The event has been recorded and will be posted on the website of Serbian Association of Earthquake Engineering. We have a YouTube channel and we are posting all events. So I would like to start by introducing, first of all, just to say about the topic, very few words, because there will be lots of discussion. I would say that this topic of historic or preservation of historic masonry buildings, unreinforced masonry buildings, is not very well covered in Serbia, preservation from earthquakes. There is a concept of conservation, preservation from the effects of the weather and other aspects. However, preservation from and protection from earthquake effects is not very well developed in Serbia as a country, unfortunately, at this time. There are several reasons, including shortage of funding and initiatives to do something like that. So for that reason, what we have done in this ADRISEISMIC project is interesting because it gives opportunity at least to understand what are the tools, what are the approaches to do so. However, it's interesting to learn from other countries where these buildings of that type have been exposed and have been severely affected by an earthquake. And it's good to learn these lessons and what needs to be done in such a situation, and as well as how those countries are now preparing for future earthquakes. So one of them is New Zealand, where damaging earthquakes affected many unreinforced masonry buildings in Christchurch, in Christchurch area where our speaker is coming from. So with this, I would just say a few words about the speaker. It's my great pleasure and honor to introduce my good friend, colleague, long-term colleague, Jitendra Bothara. We know each other for more than 30 years. And he's originally from New Zealand, but in early 2000s, he moved to, he's originally from Nepal, sorry. But in early 2000s, he moved to New Zealand, where he has been working as a consulting engineer. First worked for a large company, Becca, international company for the whole, that covers the whole region, then for Miyamoto International, and now he's so works on his own. So Jitendra has specialized in masonry structures, particularly stone masonry buildings, but he has worked in other areas, of course, of structural engineering. And he has been very, I would say, intensely involved after the earthquakes in New Zealand as one of the experts in the field, and particularly worked on historic buildings at that time. And he will share some experience from the impacts of the earthquake and all the policies and activities that helped bring the situation together. Thank you very much, Jitendra, for coming, and please go ahead. And now just let me prepare this for you. Just go out. So Matija, I'm not sure how you, can you maybe see, I think this mouse is not going further away. So please, it's because my presentation is. Yes. So to switch to okay.
Kia ora, namaste, and good morning. Thank you for inviting me to share some of my observations and experience on unreinforced masonry buildings, a structural system which has become untouchable over the time. If you look back before Second World War or First World War, most of the buildings, even large buildings, were constructed in even this building. I guess, as masonry buildings. Then came concrete and steel, and over the time, masonry buildings became obsolete practically. So though I say it obsolete, still I think, I guess, based on various literature, there are more than 60 to 70% buildings around the world are masonry in this form or some form. And if you look at the earthquakes, 2005 Kashmir earthquake in Pakistan, or recently 2015 Nepal earthquake, or any other earthquake, Chinese earthquakes, you see a lot of damage and destruction and death is due to the masonry buildings, because we have not invested on these building types, despite there being a sheer number of large number of buildings around the globe. But we forget these building types, and practically, I would say these building types have become like a primitive structural system, which are dirty, unsafe, despite 60 to 70% people living in this type of buildings. So I will be basically sharing my observations and my experience working in Christchurch and in general New Zealand on this type of buildings. Of course, I'm working on many all type of buildings, whatever as a consultant I get, and I'm involved in many things, but I will basically focus on masonry buildings only and what lessons we learn. Thank you, Svetlana, for the kind introduction. So let's move on. I would like to acknowledge the material I'm presenting is have been retrieved or pulled from other sources. I have tried to acknowledge them, but sometime I may have missed. But that doesn't mean that material is mine. But before you like to know where New Zealand is, it is I think the farthermost point from here on the earth, most likely other than Antarctica. Almost you have to go 180 degrees anti-clockwise or clockwise, and then 90 degrees north to south. So you can't go any further than that. And we call ourselves, we are at the end of the world because there is nothing after New Zealand, because only Pacific Ocean. So, do you have a pointer? So, if not, not a problem. Okay, yeah, that will be great. So basically, Belgrade is here. I am coming from somewhere here. So that's the furthermost point. But New Zealand is basically divided into two major islands, North Island and South Island. If it's working, that's okay.
Online people will not see. Try to
online.
stand close.
Okay, I will use the mouse. Okay. So in this presentation, we will talk about 2010 earthquake sequence. We do not say 2010 Christchurch earthquake. We rather say Canterbury earthquake sequence, because Canterbury is a region. So we call it sequence. I will talk about that later. We'll talk a little bit about ground motion, but my focus on this part will be more to talk on the uncertainty of ground motion and what New Zealand approach has been traditionally and historically. Then I will talk about a little bit about damage and destruction to masonry building. I will only focus on masonry buildings, though I work on different type of things. And then reconstruction recovery. And then I will talk on policy intervention. And when I say policy, it is basically politics. And as I work more and more in different cultures and different countries, disaster recovery, I find it more political, more than technical. New Zealand has some 5 million population, so it is a small country. Area-wise, it is something like 300,000 square kilometers, but the population is 5.2 million or something. So there are not many people. There are more ships in New Zealand than people. Maybe more cow now than people. Why we call it sequence? Basically, the earthquake started, first earthquake, the major earthquake was on September 2010, magnitude 7.1, but it was little away from Christchurch city. So it didn't do much damage, no destruction, some damage to masonry buildings or some simple buildings, but nothing major. Then came 26 December, Boxing Day earthquake, small, but it was near city, but not much damage. Then came magnitude 6.3 earthquake. Appears magnitude sense small earthquake, but this is the earthquake which caused major damage and destruction to Christchurch. And then there are 13 June earthquake, but no casualty or major destruction. Most of the destruction was on 22 February 2011 earthquake. From 2010 to 2012, something like 14,000 aftershocks spread over a large area. And these are small earthquakes, large earthquakes, 2 magnitude 3 earthquake or magnitude 6 earthquake. That's why we call it sequence rather than a major earthquake, because usually after a major earthquake, you have few hundred aftershocks, but I'm talking about 14,000 earthquakes or aftershocks. So we call it sequence. I think it is unprecedented in earthquake history, the number of aftershocks. And there are a lot of damage, ground failure. So this is a magnitude 7-point earthquake, epicenter. And this one is 6.3 magnitude earthquake. And this is city. So practically, it is some 5 kilometers away from city center, east, 5 kilometers east from city center. And it's all occupied area, all settlement, like suburbs. And then it has a directivity towards the city. So it hit very hard the city. So other thing I would like to mention is these are hills. These are all volcanic hills. Maybe built 50 million years ago or something, I don't know. But this is all flat area. And this is all flat area. This is Southern Alps. And so this is all flat area, and Christchurch was a marshland. Some 150 years back, when Europeans migrated to New Zealand, they drained water and then settled Christchurch. So the ground is very, very soft. And many areas of craters. If you dig half meter, there's water, groundwater. So groundwater is a very close, very soft soil. And that's one of the major reason of damage. Other thing, most of the damage, the ground failure was in this area. So most of the buildings suffered damage due to ground failure, not the shaking damage. But if you go in the hills, these hills, they're all settlement, but not big building, residential houses. And these suffer damage due to the shaking damage. And you can, at a glance, you can feel the difference. The settlement damage, ground failure damage, and shaking damage. Interesting thing is, we are expecting a very large earthquake along Southern Alps. This is Southern Alps. And we are expecting very large earthquake, magnitude 8+ earthquake in Southern Alps. So this area is very heavily instrumented to record ground motions. Southern Alps didn't come. The Christchurch earthquake came from, or Canterbury earthquake sequence came from blind fault. And then you can see, because it's very heavily instrumented, we are able to record the ground motions. And you can see the ground motion, the differences. So this is very close to epicenter, and vertical ground motion is more than 2G. And in this area, the stones were thrown out of their crater because of very high acceleration. And horizontal ground motion is something like 1.5G in rough order. This is a peak ground acceleration. But as you go 5 kilometers away, something like 4 or 5 kilometers away, it has totally, practically decimated. It has attenuated, It has attenuated, and you can see very small, maybe half G, 1G type of thing. But here still you have very large vertical acceleration, we don't know why. But this area you can see within 1 kilometer, these instruments, even 1 kilometer, the difference in horizontal and vertical acceleration is more than 2 times. If you look at the spectra, both frequency content and the accelerations are different. I'm not talking about the only acceleration, I'm talking about the even frequency content within 1 kilometer, similar ground type, that's how we thought, there's totally different ground motions. So that shows the uncertainty involved in ground motions. I'm not talking about the building itself or structures, uncertainty involved in material and construction and technology. I'm talking about the ground. Within 1 kilometer, there's totally different ground motion types. And the ground motion, if you look at the spectral acceleration, was even more than 2,500 year return period earthquake. So it was very intense, but it was not very long. There are 2 things. One is very intense and long, but it was not very long. It was like an explosion. But it tells the uncertainty involved in ground motion. And within 1 kilometer. So the message is earthquake forces, because the ground motions are very uncertain and very undefined. That means whatever earthquake forces we design our building or structure for are far more complex and undefined. And our codes are very, very simplified. Though the ground motion within 500 meters are so different, our code does the macro seismic zones, and we consider hundreds of square kilometers area as same seismicity, which we have seen it is not. So we need to be aware of this, and that was a very good lesson because everything is recorded. Of course, there are a lot of ground failure, and during 7.1 magnitude ground moved by something like 3.8 meter. And this is a local highway, road, and rest. But the volcanic rocks are not very, volcanic hills are not very strong. So a lot of landslide and rock failure. And cliff failures. And these houses are multi-million-dollar houses. In New Zealand, we live in small houses. apartment is still not very common other than in big city centers. People live in 1-story, 2-story houses and all made of timber. And I live in timber house. And that's a common tradition, building type in New Zealand. And these are more than $1 million houses because of beautiful view. And you can see all the cliff collapse and many of the buildings are just hanging in the cliff. And then you see these ship containers. After the earthquake, these containers are extensively used everywhere to protect roads from the cliff failure, to protect buildings, and I will show you a few more examples. I think once upon a time, it became capital of containers. Everywhere you go in that city, everywhere containers and cranes. See a lot of, you can see the ground failure, the rock failure, and cliff failure, all types of failures. So that's near the hills. But when you go on the plains, because the city is on the plain, it's all liquefaction and ground is spreading. And this is not flood. This is all liquefied water from the liquefied ground. And few area ground settled by a meter. And I will come to that. And you can see the sinkholes, the volcanoes, and the whole car went down. So how massive it could be. So there are some examples of little soil spreading. And for example, river banks moved closer because the ground is spreading and due to the gradient. And so you can see the example of these, how it's crushed due to compression. Once upon a time, it became like a what you call monument of earthquake. But then City Council decided to remove it because of health and safety reasons. Many areas of Christchurch which are not prone to flood is now flood prone. Every time there is a major flood, part of the Christchurch goes under flood because the ground settled by half meter, 45 centimeter, a meter in few areas. And then the river bottom came up because the ground moved from both sides. So a lot of flood problem. So when we talk about earthquake, it's not only earthquake, it has a lot of side effects, the secondary effects. So when we think of big picture planning, not the one building planning I'm talking about, big picture planning, we need to think about what are the other consequences of the same shaking. So these are map of different type of ground failures and a lot of liquefaction in this area. You can see this river is meandering. So a lot of liquefaction in this area. So this area has been declared red zone. We call it red zone. So all the settlement from this area has been removed and now turned into green area because very heavy ground failure. As I mentioned earlier, not all buildings suffered structural damage. A lot of buildings suffered damage due to ground failure and unequal settlement of building. And so when you go in the building to investigate the damage, you can see difference between earthquake shaking damage and settlement damage. And a lot of buildings look perfectly well in general. But then you see the leaning by 20 centimeter or 30 centimeter. You can easily, you stand in front of a building and you can easily see building is leaning. You feel it. So these buildings has to be removed, though there was no structural damage. This building has to be removed. Some buildings are re-leveled, but larger buildings have to be removed. So the message is, ground below the building is equally important as that of building superstructure. And generally, that's my observation, and I could be wrong. This earthquake engineering is driven by structural engineers who are more interested in superstructure and go up to the foundation and then they stop. And they think they have done a great job without realizing the work we have done is not good enough because we didn't look into ground. So it's a very important to look into ground as we look into the superstructure or the structural side of the building. So after the Christchurch earthquake, there's a practically a movement in New Zealand that any work we do, we must communicate and talk with geotechnical engineer. Generally, and many other countries I have worked, geotechnical engineers are like appendix to structural engineer. But now in New Zealand, they are coming in more together. So when we work, we talk to them and we communicate, because we know far, we means not only we, means structural engineers, even geotechnical engineers know far less in uncertainty term than we structural engineers. Because there are too many uncertainties in the ground, whereas we have a lot of control. And I think earthquake safety requires risk-sensitive planning. And that's why in Christchurch, they turned certain part of the city in red zone, where they thought it's no good for future settlement, and it has been removed. So with this ground failure and the uncertainties involved in the ground shaking, let's move to the building now. So this is city center. In city center, typical of any city, there are high-rise, there are high-rise buildings, but not many, maybe few, 20 or something, because Christchurch is it is in South Island, and population of South Island is very small, something like 1 million. Now it could be 1.2 million, and it's something like 150,000 square kilometers, and 400,000 people live in Christchurch. So of course, there's a lot of space, so there's no need to go up. The people go horizontally rather than going vertically. And that's why there are not many big buildings, or not many big buildings, but many have been demolished. If you come Christchurch, I think there are 4 or 5 buildings altogether left, which are more than 80 stories or something. All other buildings have been demolished. So basically, this city center, here the tall buildings, and then mostly masonry buildings. The masonry buildings are mostly pre-Second World War or pre-60s. After unreinforced masonry, legally unreinforced masonry buildings stopped in New Zealand after 1931 earthquake. There was an earthquake in North Island, in Napier, and a lot of damage and destruction, and thereafter they stopped it. Legally, it was by me. So no masonry buildings. So all the unreinforced masonry buildings were pre-1931. But not like tall high-rise like here I see here, something like 8-story, 9-story unreinforced masonry buildings constructed pre-war. We have, I think, the maximum height building was something like 4 or 5 stories. And then there are some unreinforced masonry building in this area. Sorry, this area. This is a harbor. That's where the Christchurch started, but it's across the hill. After the earthquake, 2 issues become major. One, how to stabilize damaged building, and how to demolish or deconstruct damaged building. So de facto, it became capital of ship containers and cranes. Everywhere cranes. And rules in New Zealand are very strict for health and safety. So you have to follow protocols. You just can't go and demolish a building. So a lot of containers you see, these containers are here just to stabilize this Greek Orthodox Church. And you walk on the street, you see both sides, a lot of containers just against the buildings. And of course, a lot of deconstruction. This is other church, this is a center of Christchurch, and that's now under repair and retrofitting. So after 14 years of sequence, we are still working on reconstruction as I think a long shot. And especially urban earthquake recovery or disaster recovery is very complex and difficult, and it requires a lot of capital. Because the buildings are mostly pre-50s or 40s, so there is no understanding, there was not understanding of seismic gap and pounding between buildings. So all the buildings are together in a row without any seismic gap. Over the time, buildings changed. So there became different type of buildings in same row. Some are tall, some are low, high, some are low, and different type of buildings, some masonry buildings, and next to it is a concrete building. So when you have different type of buildings, of course, the pounding, hammering damage is much larger. And that's what you see. A lot of pounding damage to these buildings. This building hit this building, and you can see damage. And similarly, you can see a masonry building next to other low-rise building and almost broke it. As I talked earlier, it's like a sequence. One earthquake, then next earthquake, then next earthquake. So it is like a laboratory testing, as we do on shaking table testing, because we start from very small shaking, then we start keep increasing the shaking and see how the building performed over the time during different shaking. So 2010 September earthquake, and you can see some damage. Came another one, and then came another June 2011, and you can see how damage progressed. So a lot of buildings degraded over the time, because one shaking, second shaking, third shaking. So it became very interesting to go into the city, in that area, or different part of town, to see what damage that particular event has caused to that particular building, if you have records from the past last earthquake. Out-of-plane failure was one of the most common form of failure, because in New Zealand, masonry buildings have typically timber floor diaphragm. It's all timber floor. Concrete floors are not common. It's all timber floor. So when you have a timber floor, they are sitting on the wall due to gravity. So practically, floor is not holding the walls. Whereas here, I see most of the buildings have the floors, at least floors, made of concrete. So concrete holds the wall, whereas the masonry doesn't, because of the lack of friction. And then you have joist in one direction, the other wall in the other direction is free totally, spanning between the walls or working as a cantilever. So that's why you can see how walls collapse during shaking. Similarly, here you can see all the walls collapse, and you can see mangled buses, because this is a bus route, and then the buildings collapsed, the walls collapsed on the building, and the building, a lot of people died in these buses. These are tourist area, used to be. In New Zealand, cavity wall is very common. Traditionally, it used to be very common. So this is a structural wall, and this is, we call it cladding veneer. And usually this is tied with the structural wall, because this wall is 230 thick, this is 115 thick. But what we found after the earthquake, because these buildings were by then 70 years old, 80 years old. So most of the ties were already corroded. The ties, they installed ties, but these were all corroded. And in many cases, there were no ties. So this veneer was too thin, and then they just toppled. A lot of parapet failure. You walk on the street, you see a parapet failure everywhere. And the unfortunate fact is the magnitude 7.1 earthquake, that was the first earthquake in the sequence, the major earthquake event, it was in nighttime, something like, if I recall right, something like 3 o'clock. And at that time, people were sleeping in their home. But we live in small timber houses, not the apartment buildings or big buildings. Big buildings are mostly for office, other than in city centers. So people were pretty safe. And there's earthquake, some damage here and there, some cladding damage in the house here, but nothing major. But this February earthquake was in afternoon, and is a common practice in New Zealand. In afternoon, people go out of office for a walk. So people are walking on the street, and then came earthquake, and the parapets and the facade fell on the street. So that led to, I think, death of something like 35, 36 people. Total death was 185, Out of that, I think 35 or 36 people died on the street due to falling parapets and facade. And I see that could be an issue here also as I walk on the street. Other issue I see we observed was gable walls. And gable walls are at the top of the wall, so very high amplification, and they just topple. And it is not only Christchurch earthquake, any earthquake you go, you find a lot of failure of gable walls. So these are, we call them local failure. The outer plane failure, gable wall failure, parapet failure, we call them local failure because they usually do not lead to total destruction of building. But then comes in-plane failure. So if the earthquake is in this direction, these walls are in-plane walls and these walls are out-of-plane walls. So out-of-plane walls topple first because of very low stiffness or very low stability, whereas in-plane wall has a lot of capacity or stability. So a lot of type of damage. One of them very common was diagonal tensile failure. And you can see even the bricks have been broken. This is, I think, one of the tallest masonry building in Christchurch. Of course, it's demolished, but 1, 2, 3, 4, 5-story building. I think this was the tallest building. So a lot of diagonal tensile failure. Or sometimes people call it diagonal failure or shear failure, but I don't think using term shear failure is right because even bed joint failure is also a shear failure. A lot of sliding failure also. So this upper story of this building moved by practically 200 millimeters. So the ground floor is there and upper story wall just moved by almost 150 to 200 millimeters. And they were not moved like this, it went like this. So that was very interesting to observe. And of course, this also looks like diagonal tensile failure, but it is not. Because you can see mortar is very weak, so it is just sliding rather than forcing bricks to fail. If once the bricks have failed, like last slide, there is no going back. And over the time, after a few cycles of shaking, we lose load path. Whereas in this type of sliding, there's a lot of energy is released because of the friction. But over the time, of course, it will degrade and brick starts falling. As you can see, the brick started to come out, and after a few cycles of shaking, this will fall, and then the wall start crumbling. Rocking and toe crushing. So you can see upper story has not much damage, whereas the ground floor, these piers all rocked, and then that led to toe crushing of the piers. We have a lot of arches, used to be a lot of arches in the buildings. That looks beautiful, but the arch suffered very badly. One of the major cause of damage, I think, was diaphragm failure. And diaphragm was not able to hold walls together. The diaphragm, floor and ceiling, roof are like a lid on a box. And the lid was not able to hold walls together. And that led to out-of-plane failure, a lot of out-of-plane failure of walls of a lot of buildings. And you can see, even in this building, the diaphragm moved more than a meter. This building is something like 40 meters long. And it is something like more than a meter diaphragm moved. So you can see the deflection. No wall can, masonry wall, even concrete wall can't sustain this level deflection. So of course the wall failed. There used to be a lot of chimneys all around Christchurch, everywhere chimneys, because it's a cold place. In winter, temperature can go -5, -6 degrees centigrade. So a lot of, that was the main source of heating traditionally. But now we mostly use heat pumps, or we call it heat pump, like air conditioner unit. That's most common. But traditionally, it's all fire or chimneys, and most chimneys collapsed. So if you come to Christchurch now, you still see a lot of chimney, but these all are fake chimneys. They are not true chimneys, because they just constructed it back so it looks like an old house. It could be still functional, but it may have a flue inside. And we don't use fire anymore. Mostly we use heat pumps. And sliding of tiles. Here I see tile everywhere. Tile looks beautiful, far better than metal sheets. I think tiles looks fantastic, but during shaking, these tiles could slide. They look non-structural, and most engineers would say structural, oh, that's a non-structural item. I don't care, but it can kill somebody. If falling from a 3 meter or 4 meter height, it can kill somebody. And philosophy or the ultimate goal of earthquake resistant design is not to save building, it is to save people. So we should be looking at holistically on each item which can kill people, including tiles and appendage and other items. So that's about the different type of damage to building structures, the masonry building structures. Traditionally, in New Zealand, there is a focus to strengthen unreinforced masonry from 60s. So it started from 60s, but it was up to the local government, that means local council or municipal council, to implement the act or the legislation. So some councils were very strict and they implemented it, few did not. It was voluntary. But it started in somewhere in 60s. So for example, Wellington City Council was very proactive from very beginning. Whereas Christchurch was a bit slow and laid back and let people think what they want to do. Though a few buildings were strengthened, not a few, many buildings were strengthened, but not all. Whereas Christchurch City, Wellington City Council required all masonry buildings has to be strengthened from 60s. But the interesting thing is, this big masonry tower may be 10 meters tall. There are, you can see concrete bands or concrete beams. These even are not complete. This one is complete, you can see, going all around. So the walls collapsed above the ring, but these rings are not complete. They just go up to here, it is up to here. Still, it was able to tie building together. Though there's a lot of deficiencies, and you can see a lot of damage, cracks. Here, where the beams, you can see a lot of damage. But the important thing is, these bands or these beams are able to hold walls together. So even if there is a deficiency, it made it purpose. And that's what the important thing is. Then there are a lot of deceiving type of thing. The fake beams. So when after the earthquake, I was there, and our part of assessments we were doing, and I was very surprised to see this building on the right. And I thought, it has so many bends, why is this building damaged? And then I realized these are all fake bends. These are all bricks, and these are all cosmetic plaster all around. So it looks like beam, but it is not. So when we do assessment of building, we have to be very, very careful. What is a true, what is a fake? And interesting thing is, and I find as I work as a consultant and other things, I find people spending enormous amount of money. They spend an enormous amount of money to make their new building look old. And then there are other people who spend enormous amount of money to make their existing or old building look new. And that's what they are trying to do, to show a lot of design. But then as it's structured, oh, there's a band, 1, 2, 3 bands. It's a good building. It is not. So we have to be very cautious about when we're reading buildings. And when we read buildings, the interpretation could be very different. After the Christchurch earthquake, of course, it was a big event. So no manpower, no country can prepare manpower required for recovery and reconstruction for a major event. No country in the world, as far as I can think of. So of course, people come from other places to support or work. So a lot of people from Europe went, Italy and UK and other countries, but they didn't know New Zealand building system. So I was talking about residential buildings and the one-story timber house, but outside cladding is brick. So people coming from Italy, they thought that's a masonry building. And that's what they wrote in report. And I was working there, so once I saw the report, I thought, oh, what is happening here? So these gaps always remain, and we have to be very cautious of these things. This massive building, stone masonry building, strengthened by post-stressing the walls and performed very well, very little damage. This building has been further strengthened after the earthquake, but this photograph is from pre-earthquake and very little damage. And you see this all steel strips done maybe in 80s or something or 70s. And all these buildings survived very well, very little damage. And the buildings which were not strengthened, people didn't do anything, they suffered very severe damage. And you may think this is the first element to fall from the roof, from the top of the building because of very high amplification. But all this you can see perfectly standing because they are tied from the back. As part of the strengthening of the building, they also tied these appendages, these elements, artifacts also. So when we do strengthening, we need to think, or even new construction, we need to think holistically what could fall and kill somebody. So they tied everything and it performed extremely well. This building was under retrofitting after the 2010 magnitude 7.1 event. And then came the February event. They had not finished it. And you can see it is a very interesting observation to compare things. They strengthened this part, still standing, and this part they were to strengthen, it collapsed. This is other element, other building, which was under strengthening after the magnitude 7.1 earthquake. And they put these beams and everything at the top, and then came February event, and whole parapet collapsed. Because now they had put beams, so everything collapsed together, become more vulnerable. So when we are thinking of retrofitting or any intervention, we need to think what could be the consequences if it fails. Earlier, it may have been a local small damage, but now it's a much bigger damage because the work is not completed yet. The chemical anchors didn't do very well. They performed extremely bad. Their performance extremely bad. The reasons were usually holes were not clean when they put epoxy. They drilled but didn't clean very well. They didn't clean properly. Sometimes the epoxy was not enough, and many times even whole brick was pulled out because the anchor was in one brick, so whole brick was pulled out. And you can see bricks hanging from the anchor, wall is gone. You can see whole plate is pulled out. One brick is hanging here, a brick is hanging from the anchor, but the wall is gone. So these days we mostly use through anchors only. But there are some deficiencies with through anchors also. For example, puncture of wall or breaking of the tie. And sometimes even this road plate, we call it road plate, I don't know what you call it. It was broken because they're made of cast iron. But my observation after the earthquake was through anchors generally performed well, whereas the chemical anchors didn't do well. And height, and of course, mechanical anchors are no good because of the expansion. They split the brick. So the chemical anchors are better, but the chemical anchors are very sensitive to quality control. Very sensitive to quality control. If you cannot maintain quality, then it's better not to use chemical anchors. Through anchors are much better because it goes through the wall, so it is holding whole wall together. So again, the message, sorry. Yep. So even small, well-thought intervention can save building. So if it saves building, that means people are also protected and the property is protected. So I'm not talking about very big, massive intervention. Even small things work. If you think judiciously and very carefully, where is the problem? So now post-earthquake intervention. Earthquake happened, so what next? So after the earthquake, government of New Zealand government constituted a royal commission to investigate and report on why buildings suffered so miserably, why 185 people were killed, and what could be the legal best practices required in law and the practice that could improve our building stock. And then there is a very extensive study by the Royal Commission, investigation by Royal Commission. And so they gave a big set of recommendations. And for last 10 years, we are implementing these recommendations. So these recommendations brought changes in New Zealand law, especially building law, building consent process, even many building standards have been changed to address the recommendation of the Royal Commission. I will not go into detail, but I will talk a few. A change came in Building Act because in New Zealand, all buildings other than small residential houses must survive a moderate level of shaking. I'm not talking about 500-year return period earthquake, because that's a design earthquake. I'm talking about moderate level of shaking. All buildings must survive moderate level of shaking. And moderate level of shaking is interpreted as 1/3 of what is required for new building. In simple terms, if we design today, exact same building if we design today, and our base year coefficient is 0.3 G, or base year coefficient is 0.3, then this building must have, because this is an existing building, must have strength, must have capacity 0.1. That's 1/3 of new building. I hope I'm clear. So that's required by Act. When I say capacity, it's both strength and deformation capacity. Because in an earthquake case, deformation capacities are very, very important. So all building must have 1/3 of capacity of new building. So if the capacity is less than that, building has to be strengthened. That's a simple law, or it has to be removed. That's required by law. So the law came in 2004, and it was implemented in 2004. But after 2010 earthquake or earthquake sequence, it has amended to address the new understanding of the earthquake. So there are some changes made to the law, but that's the minimum required. So so that means City Council does the assessment, preliminary assessment of the building, preliminary. And then they identify it has capacity less than 1/3 or more than 1/3. So 1/3 is now interpreted as 34%. So if the capacity is less than 1/3, the building owner is notified that your building is less than 34%. Please prove it's more than 30%, 34%, or advise what you want to do. Then the building owner has to come with a plan. So they hire an engineer to do a detailed assessment. If they can prove it is more than 34%, then they don't have to do anything. If it's less than 34%, building owner has to give a plan when they want to strengthen the building or if they want to remove. And then City Council will typically give 10 to 20 years time to retrofit. So when I say 10 to 20% years, it looks very large. And you think, why building? There could be an earthquake tomorrow. Building could collapse, kill somebody. So it has to be better we strengthen today, not tomorrow. But the strengthening or retrofitting doesn't come free. It costs money. And you have to organize money. And many times it could be millions of dollars. So of course, we have to find resources. And so that is accounted for. We all worked on this, how we address this issue. So we know there is a risk, but still we say, okay, 15 years time to retrofit the building. And the other reason is, when my experience working on retrofitting of buildings is, when we retrofit building, there could be substantial cost of making it good, because when you are adding few columns or some walls or ties or whatever, then you have to make it bad. You have to break it. Once you have installed these elements, you have to fix it again. And that cost of that fixing back could be significant. Many times I found could be at the par, the cost of the making it good could be at par to retrofitting cost. If you don't have to fix building, it's much easier. But you have to live in this building. That means you have to make it good. And the typical cycle in New Zealand of renovation of building is 10 to 15 years. People usually paint their building in 10 to 15 years time. Paint and renovation, change of use, a lot of things happen. So people can put their retrofitting plan together with renovation of the building. So they save money, they don't overspend money. Because if you push it very hard, it could be a disaster. It could be a financial disaster. So we have to think, safety is not free. It costs a lot of money. Moving on. So now we have to do assessment of the existing buildings. So when I say assessment of existing buildings, means we need some certain rules. I have to move a little faster. Sorry, I'm going to soon. Okay. So we developed a set of guidelines, and I was very fortunate to be part of this. I was one of the co-authors of writing all these guidelines. So, and New Zealand approach typically has been be simple. And what we say is be right, not accurate. So that's a basic philosophy of New Zealand design. Be right, it is not necessary to be accurate. So we don't believe in accuracy, but we believe if it will work in general at a high level, it will work. And as I mentioned earlier, even in half a kilometer radius, the ground motions are 2 times. So even if you are accurate, what you are designing for, we don't know. So what is the point of being very accurate? So we don't focus too much on accuracy. And that is the focus of these guidelines. So we had general philosophy, and then assessment procedure, earthquake demands, geotechnical consideration, concrete buildings, steel buildings, and different type of buildings, masonry, timber buildings. And so I will talk about unreinforced masonry buildings only today, not another type. But it's a whole set of documents, and it's free to download. Good thing in New Zealand, a lot of things come free. We pay tax. So government gives us free. So you are free to download, you don't have to pay.
And the link, I include the link.
Okay, flyer, okay, that's good. And it is written in a very practical way. You will find not much theory. Though these are standards, these are binding by law. These documents that I'm presenting here are binding by law, like a building code. But they are written in a very simple way rather than in legal language. So, for example, if you go to ASC 41, there's a seismic assessment of buildings. It focuses a lot on testing of material. We don't talk about that because we know there are too many uncertainties involved. So unless it is a critical, you can go by default values based on some testing. Testing done by somebody else in university, PhD students, and there are others did a lot of testing, and they developed some guidelines or some framework, and we just used. And if there is something critical, then we recommend for testing. Because we think rather than spending money on testing, it's good to spend money on retrofitting the building. And we use probable strength for assessment, not the dependable or not characteristic strength. And these guidelines that I'm talking about, masonry buildings, there's a C8 is for rectangular units only. But we have not covered block masonry, but you can do little meter modification you can use for unreinforced block masonry, concrete block masonry. So out of plane failure. So if the wall is, this wall is held at the top and at the bottom, so it is spanning vertically. So when is the earthquake motion, it's pushed out or in. And we are holding it. So it's based on the cracked section, and we assume these walls will rock because they are held at top and bottom, so they will rock. So the all formulation is based on rocking of outer plane wall. So we don't rely on uncracked strength. That's one thing. And for example, if you go to ASC 41, it gives you ratio, height to thickness ratio to assess walls. If you are less than that ratio, you are okay. Whereas we give whole set of formulation. So you can calculate it depending on your boundary conditions. So it identifies boundary conditions. And then also that guideline also includes a lot of plots. So you don't have to do long calculation. You just go to plot and say, okay, height to thickness ratio is this much. This is my boundary condition. These are my vertical load. Because with increasing vertical load, wall will be more stable. So this gives parameter, and then you can pick up the number. If the number is more than 34% in New Zealand context, you don't have to do anything. But if it's less than 34%, and law requires it has to be more than 34%, now you have to strengthen the building. In plane walls is a typical figure I took from Webb, basically rocking and toe crossing. So basically these are flexural rocking type of failure. They are more stable mode of failure. Bed joint sliding and diagonal tension failure are shear mode of failure. But I think these three, 1, 2, and 3 are, sorry, 1, 2, and 3 are more stable mode of failure because still you have gravity load path. Whereas the fourth one, this diagonal tensile failure, once it happens, brick starts crushing, you will lose the load path, and you don't have going back and forth, so gone. One cycle, this direction cracking, other cracking is over. Whereas if it's a sliding, it keeps going for very long, keeps going, and we are releasing energy through damping and all sorts of things. If the spandrels are not very deep, then spandrel failure is very common, as I presented in few photographs. So it has to be taken into account. But if the spandrels are very deep as compared to the piers, then usually spandrels just act like a deep beam sitting on piers, and then something like this, and they just rock or diagonal failure or sliding failure. And that's what we observed in these earthquakes. In the meantime, as we are working on 2010 earthquake sequence, improving buildings or fixing, strengthening buildings, came 2016 earthquake. We call it Kaikoura earthquake. It's near Wellington, the capital city. In Wellington, still there's a lot of unreinforced masonry buildings. So the government brought in something like ordinance. It is not law, but it is a mandatory that people have to fix all their parapets and the facade, like intermediate strategy to reduce risk, because the parapets could fall and kill somebody on the street if there's an earthquake. So it is like an intermediate strategy to fix buildings. But if the building globally is less than 34%, they have to fix whole building anyway. But after the earthquake, government gave, I think, 1 year, 2 years to fix all the facade and parapets. And even in that time, there were not enough people to fix these things, not enough engineers. Engineers are there, but mostly crafts people, builders, not enough. And so people struggled. So when we think of this strategy, we also have to think where the people will come from. Who will fix them? Is it to make law and writing guideline or a code is one of the easiest things in my opinion. But implementing that in real field is really difficult. Requires a lot of energy. So a lot of building has been strengthened after the Christchurch earthquake, for example, for out of failure, this strong back has become very common. And a lot of buildings have been revived, which were not in use before the earthquake. These are practically obsolete, abandoned. And now these buildings have been revived has become beautiful cafe, shopping area. So a lot of buildings have been revived. People are going back maybe 60 years, 70, 80 years, and think, oh, these buildings look beautiful. So the parapet is strengthening of their 5-story historic building. There are a lot of parapets, though they were strengthened, they fell in crisis. The reason is parapets are like this, and there is this diagonal strut. So when there's a big vertical motion, an earthquake moving horizontally and vertically, so sitting like this is like vertical motion and moving this, so you see it move like this. So parapet was practically in the air and it fell. So because there are no tension capacity, because once you put diagonal here, there's a big tension here. So now we require to put a tension tie also. Looks very simple, but we didn't know. And we engineers think we know everything. It appears we don't know most of the things. The skyline of Christchurch has significantly changed. This is one church before the earthquake. Now it looks like this. Even this one, you can see how the whole layout, street layout has been changed because the government took it an opportunity to improve layout of the city. A lot more open space. This building collapsed, and now all these buildings have been removed. It's a big park now here. So a lot of open space. So in my opinion, it's very important to know where we went wrong so we can fix things. Now, coming back to your own city. So I thought I should put a few photographs to see what I expect based on my observations. With Svetlana, thank you. You took me around different part of the city, and I took few photographs and I presented here. Hopefully it will not hurt you. Because everybody thinks, oh, he is the best. Our building is the best. But it is not, unfortunately. This building, I don't think this building requires any earthquake major event. It's almost coming out. And sometimes what happens is, when you live here, you see everything normal. Somebody outsider has to come to see, look, you are wrong here. And that happens to everybody. Many times I think, oh, I know this. But somebody says, no, you know this, but you are making a mistake. So you can see almost the facade. You don't need much. Don't need this facade. Other buildings, but sorry, I'm not trying to say these buildings are bad. I'm just bringing in enormous examples to present in technical sense. Hopefully there will be no legal implications on me. So you can see the large appendage, maybe something like 3 meters tall at the top of 3-story high floor building. So something like around 10 meters high. So the amplification would be at least 2 times or even more. And during ground shaking, that can immediately, it can easily come out because of high amplification of ground motion. Similarly, this building, Villa Pilot, you can see they're ready to come down. Somebody walking on the street comes. You don't need much. You want brick coming from the 3 meter high is good enough to kill somebody. And that's what happened in Christchurch. Parapet could fall. I don't know how well it is tied. And that's what happened in Christchurch, practically similar building, and the whole dome came down. Fortunately, nobody was killed here. A lot of chimneys. And you can see how chimney collapsed. And that could be a disaster. Looks small, but implications could be severe. Gable wall. And there is a video, I took that snapshot from a video. Actually, this man was walking here when the earthquake started and the gable fell. And this man ran. Had he been late by a couple of seconds, maybe 2 seconds, you would have been under the rubble. And gables are the first to come down. They are very vulnerable. Then RC slab, floor slab means you have less of out of plane failure, but then you have major in plane failure. And so this building is located in this direction. I think these piers are under severe stress due to in plane failure, rocking or diagonal tensile failure, sliding and other type of failure. And then you see upper part gets much stiffer. This part is far more stiffer than here. So all the deflection or deformation has to be concentrated in this part. And that means it could eventually lead to soft story type of failure. So now the conclusion. As I mentioned earlier, earthquake forces are very complex and undetermined. So it is no point of, that's how I think, no point of being too accurate. It's important to be right, not too accurate. I don't think very sophisticated computer analysis will solve much of the problem. If I don't know the building, how a computer will know the building? If I can't understand a building, how it will perform, how a computer can understand. So it is no point of being too dependent and very sophisticated analysis, but it's important to understand that in globally how building will perform. So being right is more important than being accurate. And as I mentioned earlier, well-designed, constructed, or retrofitting works very well, because earthquake, so first goal is to identify where the weakest link is. The moment it identifies the weakest point, and from there the damage cycle starts. So it is not one point, it is a starting point of domino effect. Where we went wrong in whole policy perspective and technical perspective is very important after any disaster, because it's a time to look in retrospect what mistakes we did or what we didn't do well. Because if we don't know something, now we know. So time to fix the problem. Earthquake resistant construction or any disaster recovery or disaster reconstruction is a multi-dimensional task. It is not one person's task. It is not only structural engineer can solve problem. It requires a lot of disciplines, geotechnical engineers, social seismologists, architect, and non-structural engineer, and all sort of things. But more important than is the policy perspective. If there is no political will, it's extremely difficult to do anything because it's all politics. And I worked in, I'm currently working in Pakistan, and that's my 12th or 13th disaster where I'm working for recovery. And I find it's all political. If there is no political will, it's very difficult to do. And I think we are very lucky in New Zealand. Our politicians here, and they listen us. And that's why we have changes in our policy and what can be done, what cannot be done. Of course, it brings a lot of stress also because people struggle to retrofit their building because they don't have money. And even when they retrofit building, their rent doesn't go up, their return is, there is no return. So of course, people struggle, but still things happen. So it is all from me, presentation. If you have any questions, sorry, I took much longer than I thought. I think I was more relaxed. Thank you. We went to an hour.
That's okay. Thank you very much, Jitendra, for a very interesting presentation. You really took us to New Zealand. I felt as if I were, and then you brought us back to Belgrade with not so good news. But but I believe that's really great to get a perspective. So I think since we have coffee, sorry, for online participants, we have a coffee and some refreshments outside this room. We will take a 15-minute break, and then if you have questions and if you for Jitendra and if you need to leave, you can ask after the break. Otherwise, we'll have a session for time for questions at the end. We'll try to stick to the schedule from 10:30 onwards. So we are back at 10:30 Central European time, I'm not sure which is on in about 15 minutes. Thank you very much, and we have a break. Thank you. So let us maybe just the microphone and.
Okay.
Ja da samo sa ovim teram.
Možete ovako na ove stranice, možete da klikćete.
Ja mislim da ne treba ništa da se vraćamo na onaj program, sad svako nastavlja ovoga, pa onda drugi, ja mislim da u redu. Možete kažete o sebi da
kažem nešto o sebi.
Da kažete o sebi. Da, možda je bolje tako da se svako se da predstavi ovako, da ne bi ja ću da
Good morning, everyone. Thank you very much for coming here. I appreciate your interest in preserving historical buildings due to the earthquake. My name is Olga Đurić-Perić. I grew in this building as a student and then a little bit of the academic duties. Then I went to Africa to play a good wife. Stayed there only 18 years and came back here in 2006, jointly with my husband, which is the very first time in our life. We start in a consulting company with, at this point of time, about 30 odd engineers, structure, mechanical, electrical, no public health, because that's a very difficult subject, which we can't find a solution how to do that. But SUZI-SAEE Consultants in a very short terms is pretty busy here in Serbia. We have done new buildings in Belgrade waterfront. We have been involved in strengthening of historical building here in Belgrade, but this much from about SUZI-SAEE, this much about myself. Other role of mine, which is a subject of today's meeting, is that SUZI-SAEE Consultants was the project manager. Izvinite, ovo je kafa. Was a project manager on ADRISEISMIC project. And that is the reason why I am here today, to give you in a short terms what this project is and to connect a topic of this project together to Mr. Gentai's presentation. Thank you very much for presenting us the impact of the earthquake on historical buildings and a type of strengthening them. The same subject, if not a very similar subject of your presentation, is in fact the theme of ADRISEISMIC project, which is an international project with the Serbian as one of the partners, and it ran in Serbia from 2020 to 2022. As I said, this is an international project. The lead company, the lead partner was University of Bologna. In fact, an institute in Bologna. There were several other countries, which is Croatia and universities in Zagreb, then Albania, then ourselves, obviously the most important one, therefore in the red color, Slovenia, Greece, and then two partners from Greece, University of Greece and regional Crete partner. Apart from that, it was more important that the Serbian team comprises of Svetlana Brzev, all of them are present here. Svetlana Brzev, she has given the explanation about her involvement in this project, both as a president of SUZI and a member of the Columbian University. Borko Bulajić, again present here from our university in Novi Sad. Marko Marinković, from Belgrade University, and Jovana Boroza. This Serbian team had several main objectives to study, to find data, and they consist of establishing the methodology of how to assess the vulnerability of the historical buildings, then to establish the methodology of technical and strengthening technique and a strengthening strategy, then to define the methodology of risk assessment is probably one of the weakest area of our knowledge. And the last but not the least, to develop the action plan. I think that you all will agree that that last one is the most difficult one, but we will leave that to the presenters from the team. The hard work of Serbian team, but also the hard work of the international team has been presented and to the, oops, I should have pressed the button, through the workshops. The first workshop was in December 2020, and the aim of that workshop is to introduce the public and the local engineers about the project and to collect the data. Second workshop was in June 2021 to present a reinforcement methodology of historical buildings and level of training in Serbia. A third workshop in February and March 2021 was very important from my engineering point of view is possibility of integration and innovation of the Serbian and international practice. My apologies to the other team member teams, but I'm talking as an engineer, hence this as an important workshop. The fourth workshop was to summarize all our findings, and we are very proud to say that the participants on all these workshops were local engineers and members of authorities. We as an engineer can be very clever. We can find all the very good ways of how to do the things, but our stumbling point, as previous presentation has pointed out, was authorities and money. I think I will stop with this and leave the presenters to go into detail of all our achievements that this project was to achieve. Thank you very much.
Hello to everyone. My name is Borko Bulajić. I'm an associate professor at the University of Novi Sad, Faculty of Technical Sciences, and I will talk about technical regulations related to the seismic assessment and retrofitting of buildings in Serbia. I will also focus on the results of the ADRISEISMIC project with this respect. One of the goals of the ADRISEISMIC project was to create roadmaps. Roadmaps as strategic documents, step-by-step documents, with the aim to improve the current policies and planning frameworks in each of the 6 countries, And these countries are Albania, Slovenia, Italy, Greece, Serbia, and Croatia. The final aim was, of course, to reduce seismic vulnerability and to increase the resilience towards seismic risk. And the first step was, of course, to collect and analyze current regulations that were divided into 6 groups: seismic norms, building regulation, urban planning regulation, seismic incentives, post-earthquake planning, and insurance against earthquakes. And then we had to define 5 steps. First, identify the gaps in the current policies. Then to identify the barriers that might prevent improvements in the current policies. Then to identify the possible solutions. Then to identify responsible entities, funds, and stakeholders. And finally, to select the monitoring strategies. We first started with collecting of all norms and incentives in each of the countries. And then we all did assessment and systematization of the collected norms and incentives and highlighted good practices. Here, I should mention that by good practices, we meant only those regulations or incentives that contribute significantly to the reduction of the seismic vulnerability. And for each of the good practices, we prepared sheets containing the most important data, like the name of the good practice, main objectives, brief description, target groups, if there is a reference to cultural heritage, the country in which the good practice has been adopted, and also very important territorial scale, if this was adopted for the entire country or maybe for one municipality or a region. Then also what is very important, who is the promoter? Is it a ministry or local government or someone else? And then we also did SWOT analysis, strengths, weaknesses, opportunities, and threats. And then for the highlighted good practices, we analyzed potential of replicability and scalability. Replicability means that we analyzed if we can use good practice from one country in another country, and scalability, whether we can use it for the entire country or maybe for a region, only one region or local communities. These are the results. For 6 groups, we have collected the total of 23 good practices. One was in common for all countries. This is Eurocode 8. And additional to Eurocode 8, there are seismic norms that directly and significantly contribute to the reduction of seismic vulnerability in Croatia, Greece, and Italy, urban planning regulation, good practices in Greece and Italy, seismic incentive frameworks in Greece, Italy, and Slovenia, and post-earthquake planning in Greece, Italy, and Slovenia. What was interesting that there were no highlighted good practices within 2 topics, building regulation and insurance against earthquakes. I'll explain later insurance against earthquakes. Now I will only mention building regulations in Serbia. In Serbia, we have law on planning and construction and technical regulations for building structures. The latter document is accompanied with 2 attachments. One is list of standards for design of buildings, and the other one is list of standards for construction and maintenance. The one of the standards is Eurocode 8, and it was analyzed under seismic norms. In Serbia, Eurocode 8 was introduced in December 2019, and it consists of 12 documents, which also comprise assessment and retrofitting of buildings and the corresponding national annex. The problem is that this is only, these are only general instructions for retrofit design procedures, and the annexes are only informative still. There are no detailed and very specific annexes for reinforced concrete, structural steel, and composite structural masonry buildings. Also, there are 2 additional seismic hazard levels, I mean, additional to the current seismic hazard map that we have in our national annex for a return period of 475 years. And these are hazard level for 2,475 years return period, which corresponds to the near collapse required performance. And the other one is 225 years return period that corresponds to limited damages. We don't have official maps for these 2 levels of hazards. Prior to Eurocode 8, we had several technical regulations. They all became nullified after introduction of Eurocode 8. We of course had a transition period, and some of those regulations consisted some clauses that consider interventions and strengthening of buildings. There was a problem of misinterpretation, maybe deliberate misinterpretation of such clauses. For example, there was one that said that the building after the intervention should have at least the same resistance towards earthquake as before the intervention. So what if it was not resistant enough before the interventions? The good practices that we found in other countries, there are several, but we found one very interesting. It's used in Italy. It's called Evaluation and Reduction of Seismic Risk for Cultural Heritage. It's very interesting. The problem is that it refers only to NTC 2008, which is in force only in Italy. It's not translated into English, and it's only partially compatible with Eurocode 8. The problem with previous regulations is also that the seismic hazard maps changed in different periods, and this also created sometimes confusion. As for the urban planning regulations, we have a Planning and Building Act, then regulations on the content, methods, and procedures for compilation of spatial and urban planning documents, and the Sustainable Urban Development Strategy of the Republic of Serbia until 2030. There are two good practices that we found, one in Greece, one in Italy, that practically define way how to perform seismic microzonation. The one in Greece, they are all based on geotechnical investigations and geological investigations, so it's not cheap. But the one in Greece, it requires these kind of microzonations in the phase of preparation of general town plans and urban plans, and the other one, it regards to preparation of more precise earthquake action for particular building sites. Seismic incentives, for me, this was the most important, most interesting probably part of the project, because we found in Italy three examples of good practices. One deals with national awareness campaign, which is always good, but I want to mention the first two. One allows owners of the buildings to perform some intervention with the aim of seismic vulnerability reduction. And if they spend up to 96,000 euros per each real estate unit present in the building, then they can deduct all the expenses up to 110% in the form of taxes reduction. So this is a really good incentive. And the other incentive is that the building can be increased in volume of maximum 10% in total after a certain level of seismic safety has been reached according to the type of the required interventions. So this is very interesting, how to introduce some incentives and that the people strengthen their buildings and not spend their own money. As for the earthquake planning, post-earthquake planning, we have good laws in Serbia, like the law on reconstruction following natural and other disasters. But I want to mention the catastrophe risk assessment in the Republic of Serbia. This is a document that is valid for the entire Republic of Serbia. And this, before I go to this, I will only mention that there were two good practices that we found, one in Greece, one in Slovenia, that deal directly with cultural heritage buildings. That was interesting. And as for the catastrophe risk assessment in the Republic of Serbia, the results are shown here on the left. They analyzed two scenario earthquakes. One is the most probable unwanted seismic event, and the other one is the unwanted seismic event with the heaviest possible consequences. And in both cases, they obtained that the risk is moderate and acceptable. And I don't think, I think we should be very careful with this, especially when we had this experience with Croatian earthquakes 4 years ago. there were two earthquakes, one in Petrinja and one in Zagreb. And the community in Croatia was very surprised by these earthquakes because there were no similar earthquakes for 140 years near Zagreb and for 111 years near Petrinja. And in Serbia, we had 1893 Svilajnac earthquake that in all previous seismic catalogs, this earthquake was assigned a magnitude of at least 6.4, and a recent study that was published 1 month ago, for which I was, in which I participated, we found that the magnitude can be even higher. However, in the current seismic catalog for the Republic of Serbia, the maximum earthquake in Serbia is 5.8. So these results are based on 538 historical data. This earthquake was felt up to Vienna and Slovakia. This earthquake destroyed town of Jagodina at the time. And we should be very careful. If there is a chance that a stronger earthquake than 5.8 will occur in Serbia, we should very carefully assign only moderate and acceptable seismic risk, especially after what we know about the current vulnerability of buildings in Serbia. We've seen some examples in the first lecture. Today, I've shown here on the left, this is the Google Street View of two buildings very near here, maybe 1 kilometer from here. This cannot be seen now because there is a new building here, but that is why I have pictures from a couple of years ago, and you can find this on Google Street View. You can see that this is unreinforced masonry structure with more floors than it was allowed according to our previous regulations, and with additional 2 or even 3 or maybe perhaps even 4 floors upgraded. So this is a huge risk, and I don't even have to mention what is the seismic vulnerability of this building. And we also had similar examples after the Kraljevo earthquake in 2010, where the heaviest damages were in those buildings that were upgraded or increased in volume without previous strengthening, or the buildings where there were interventions, illegal interventions that reduce seismic vulnerability. At the end, I should also mention the insurance. Real estate insurance against earthquake in Serbia is not legally binding. In all these countries that were part of this project, there were no highlighted good practices. This topic depends on the country and on the insurance company. Usually, you can insure your building against earthquakes only if the building is pre-insured in case of fire. And some of the insurance companies, they request that the building has been designed in accordance with seismic codes, but sometimes you can even insure your building even if there is no building permit or the building has not been legalized. Or, for example, in a multi-apartment building, you can insure only one apartment. And we discussed at workshops also the experience of various people with insurance against earthquakes, and we found that there is a big gap between theory and practice, because in theory, there is a rather small premium that will cover everything, and then after the earthquake, not all the damage was covered. And one of the suggestions was maybe to introduce earthquake certificates or some kind of seismic passports also for buildings. And I will finish with this. Who is responsible? We identify responsible entities, fund stakeholders, who will define the funds, who are responsible entities, who are stakeholders, and in short, everyone is responsible. Everyone should work on this. This is not a simple task only for a small group of people, only for one institution. All the government, all the ministries within the government should work on this. Institute for Standardization, practitioners, I mean, civil engineers, restorators, architects, also higher education research institutions. Everyone should work closely and collaborate on this if we want to introduce and improve our regulations that will lead to reduction of seismic vulnerability. So thank you for your attention.
Thank you, Professor Jitendra and Olga and Borko. I will now talk about shortly about the working package 3, which had the task to collect or summarize all the work that was done in work package 1 and 2. Let's say the packages that were led by Borko and Svetlana, that were, let's say, more practical in way of collecting these norms and rules, and also the things that Svetlana will present regarding the strengthening measures and assessment of masonry structures. And the idea of the project was to give some output, and this output was, let's say, aimed to have trainings and courses for all the participants being part of one strengthening project of one structure. And the idea was to use these materials that were developed during the project. I must say that the biggest part of the work was done by the lead institution, University of Bologna. And they created a set of trainings and courses and placed it on the platform. I will show you how it works. I will not go into details of all the trainings and the material because there is a lot, but it can be found, and then it can be used for training architects, engineers, public administration, which is an important part of any project that has to be approved. And also there are really good trainings, videos, and materials for the craftsmen and the workers that should at the end execute the project, and which is important because we can design whatever we want, but if there's no one who can apply it, then it will not see the light at the end of the road. So as I said, the work package 3 was aimed to prepare these courses and tools, and we divided it in several steps. First step was to summarize, to collect the data about each country, each partnering country, the institutions that are incorporated in giving the courses and training. So beside the universities and the schools, also some institutions that in some countries exist, in some countries do not exist at the moment. And then we said, okay, if these are, let's say, the capacities that tomorrow can provide these trainings that we prepared during this project, then we are also setting the amount of trainings and the level of training so that it can be applied in practice. And then we divided the trainings in the second step in 3 packages and 1 instruction. So 1 package is for engineers or architects, civil servants, and workers, and 1 instructions for volunteers. So maybe in Serbia, this volunteering part is not so let's say vivid and live, but in Italy it has a significant part in this process, and therefore it makes sense to be included. And then the third step was when we made these materials in the second step, we wanted to validate it and then get the feedback from these workshops and trainings to improve the materials, and then make them in the final form to present them to the audiences. And for example, this is just a short overview of the task 1. So you can see the numbers of institutions identified in the partnering countries. And as you can see, that Serbia is not standing so bad. Okay, Italy is really in this field, of course, far from all the others, but let's say our surrounding countries are more or less at the same level. And this is a map of Serbia with the institutions, or with the red dots showing where are the institutions. So generally, it's also good geographical distribution. And each task was summarized in a report. All the reports are public and really good it's a literature to be checked for everyone who is aiming or wanted to work in this field. And then, as you said, these target groups, so we divide in 3 target groups. Practitioners are, let's say, engineers or architects who should make these strengthening projects, and then civil servants who should prepare them for the execution, and at the end, the construction workers. Or just shortly, let's say this first target audience or the practitioners or engineers, this category. For each category, there is a clear definition who is belonging to this category, what are needed level of pre-knowledge so that they can, let's say, dive into this material and take them so that they can study it. And for example, here's a list of knowledge and skills that these materials is providing. And there's a long list, but I selected a couple of interesting ones. So it's a really mixture of survey skills so that they can first get impression of the buildings, also non-structural testings, then the management, safety measures, the IT tools, the BIM modeling, which are now more or less becoming a standard. So all this is combined in these training courses and provided to the trainees. Then the second group are civil servants, and there it's also definition of the category, their level of education, and how they can approach to the material. And for example, for them, there are 3 groups or 3 steps. First are the first group are tools and technologies that they can use, such as some systems and tools for the architectural structural survey, so that they can understand the material that practitioners or engineers, architects are providing to them. Then the management process, so managing the whole process of the technical documentation. And then, let's say, the first thing that you think when you mention the civil servants are these administrative and management skills. But of course, these are also part of the materials. And then the last group, workers, as I said, maybe the most important ones, because they are, let's say, tasked to do the final execution and really to make the projects, as I said, see the light. And they here the skills are divided in operational skills and transversal skills. So operational skills are, let's say, to understand which techniques are used for this anti-seismic structure consolidation and use of materials. And then the second group of skills is to understand the collapse mechanisms, for example, that can happen, and so that they can really understand why they're doing and why they're applying some measures, not just applying them blindly. So then the execution is much faster and more effective, of course. All these training package tools are placed on the Moodle. They are, which is really important, translated in 6 languages. Maybe sounds strange, but especially it's important for getting wider audience. So all the partnering countries have the material in their own native language. And then what is good also, before you start taking some course or training, there is a syllabus showing what exactly is part of this material, so that you can choose and see what you can expect. So for example, all of them are modular. So these trainings and materials can be also used to make custom-made training materials for some companies that are specialized in seismic isolation or strengthening of masonry buildings and so on. So the parts of the trainings can be taken separately and then combined in one training course that can be provided to different audiences. Therefore, there are macro and micro categories that are divided in specific topics and then learning units. So there is really like a pyramid of a structure of every course. So here are some details. I will not go detailed into it because of the lack of time, but there is always like introduction, level of explanation, and then examples of applications so that it can be, let's say, every course easily acceptable. And at the end of every training, there is a questionnaire or, let's say, some kind of tests with questions and answers so that the participants can, take these verification tests to check their level of knowledge. And for example, here is the example of one learning units, the slides, how they can look like, and also every slide or all the presentations have this recorded voices and or subtitles so that it can be read or taken by everyone. So as I said, these are the partnering countries and the levels or the languages that were applied or translated. And just to conclude at the end, what is the benefit of the ADRISEISMIC project for Serbia? So being part of this project consortia with the countries, especially Italy and also Slovenia and Croatia and Greece. So they have a lot of experience, we must say much more than us, and we gathered new knowledge and training materials that can be really spreaded in our engineering audience and also practitioners. So this is provided online, but can be, as I said, also combined for special tasks that are needed or requested from some companies. And for example, one of the partners in it was IIPLE or IPLE, which is an institution that has 75 years of training of civil servants, engineers, workers in different levels of public safety, health, insurance, strengthening measures. So really one good institution that at the moment doesn't exist in Serbia, but they have a lot of knowledge that they shared with us. And at the end, one of the most important results was these guidelines for the practical application of seismic strengthening. So as I said, each work package has the report, and the reports are, let's say, rather long, but they can contain good material that is easy, approachable, and acceptable by the potential users. So thank you, and I hope it was in time. Now, Svetlana Brzev.
Yeah.
No.
Thank you very much. I'm going to talk, I believe, from the first beginning. I introduced myself, Svetlana Brzev, and I was responsible for the second work package, which was related to the methodology of and also action plan, how to implement the methodology for seismic risk assessment of masonry buildings and how to implement it in Serbia. So today I will talk only about the methodology part. So the methodology, we can call it rapid or expeditious, as it is used, the terminology that's used in the project. Mostly, it's the purpose is to have a walk through assessment. So it's not about doing calculations. It's about visiting a building like Jitendra did, and by just visiting and having some information or collecting some data, there is at the back end, there is a procedure that estimates how dangerous or how much that building, particular building, is at risk. So such methodologies exist in the world, and the methodology that Jitendra talked about in New Zealand is not rapid, it's more detailed, but I believe them could be rapid as well, but in one of the most well-known methodologies is ATC20 from the US that is along the same lines. So the idea is to provide a qualitative analysis, in a short time, and it could be used as a preliminary tool to decide to select the buildings that could be further screened or not screened, but analyzed in detail and hopefully retrofitted if needed. And it could be in the context of Serbia, and I think the whole region, the most important structural systems and typologies are reinforced concrete and masonry buildings. And this methodology that was developed under ADRISEISMIC project is indeed applicable to both types of buildings. Today, we'll be talking only about masonry buildings. We are planning, or at least I'm hoping that we will have another similar seminar on reinforced concrete buildings, but likely next year. So again, sharing different methodologies. So the methodology that I'm going to talk about today, and by the way, of course, all the slides will be available on the website, so you can see what is these resources. So a paper that describes the ADRISEISMIC methodology, it was published in last year in a journal. So which is available free of charge. So anyways, now Jitendra gave a good context to this in the sense of what are the critical, or what are the possible, and then what are the critical, which are the critical failure mechanisms for masonry buildings. In general, the way in this methodology, these mechanisms have been identified. One is disintegration, mechanism one, which I believe mostly applies to stone masonry buildings. I cannot see it happening in brick masonry buildings. It's hard to imagine, where the wall just simply disintegrates, simply falls apart and falls like a pack of cards. And then the second is kinematic failure mechanisms, mostly out of plane. He again explained or showed some examples which were very common in New Zealand, that walls were falling out of plane due to out of plane seismic effects, and usually in the buildings with flexible timber diaphragms, timber floors and roofs. And then the third is due to in-plane seismic action. So that is the one that is common and could be very common actually in buildings in Serbia as well. But this methodology that we are talking about here is only focused, that's why I circled it, on the first and the second one. So simply it assumes that those will be the critical that would cause the failure. As I said, it may not be common, and the reason that the third mechanism is not included is that it really requires more serious calculations. So I wouldn't say it would be possible to do it in a rapid way. It would require more analysis. So let me go back. So this, just to get immediately a sense how this methodology has been implemented, and I will go then about the details of the topics in the methodology, is that it's all done, as I said, in Excel spreadsheets or in table form, where the input data are entered into this, and then in the back end, the calculation is done, and then the level of, so input part is the upper portion, the output or results are the bottom portion, and the results are basically an estimate of seismic risk for a building, and that is the identification which ones are dangerous or more dangerous than the others. So, so the idea, the algorithm, just as on the concept level, is that the input is given by it needs technical, the persons with technical background. It cannot be done by a tax accountant or something like that. Certainly, it is somebody who understands the questions and also has some background. It doesn't have to be very advanced, with a young engineer, architect, or maybe a student. And then analysis, all these blue circled parts are done at the back end. Analysis of data, results, and as results, I will say, and I'll show some of the results, and then we'll see application from Serbia. Three results are there: level of seismic risk, index of seismic behavior, and expected failure mechanism. So, so as an engineer architect, under seismic team, that means it's already done by somebody based on the data. So for masonry, again, as far as the input is concerned, there are slightly different, I mean, there are different input for masonry and for reinforced concrete building. So some categories are the same, but then the contents of the categories are different. So the categories of data, of input data, are general data, construction characteristics, masonry quality, obviously specific to masonry, and building data. So this is now all specific, and they are shown here in this gray shaded part, but you cannot read, of course. So general data are date of construction, or no, it's date of when the data collection is done, building address and year of construction. So those data are expected to be entered. And then this topic of masonry quality, that's actually interesting. I mean, it's interesting as far as masonry is concerned. it gives really details, 9 different input parameters. Oh, 9 different input parameters related to specifics of masonry walls. And I would say that these parameters are tuned towards stone masonry. For example, presence of headers in brick masonry. That's not, I mean, it's the nature of masonry is different. Shape of masonry elements, alignment of vertical joints, masonry element size, quality of mortar, resistance of masonry elements, and thickness of mortar joints. So this part of the input is based on, again, all parts are indeed based on different Italian methodologies that were developed over time. They were not developed at one point, and they were not developed by participants in this project necessarily, but they have been modified to suit the needs of this project and the level of, I would say, scrutiny that we were considering. So this section is based on so-called IQM method, which was again developed in Italy based on more than 20 years ago, and it's published. And for each of these, I'll just show some examples. What do they mean? And I would say that colleagues from Italy are really excellent in documenting masonry in detail. They really, I mean, Italian publications are really very, very detailed. So, for example, a horizontal alignment, you can see here in blue shaded, horizontal alignment means that whether they're horizontal rows, and you can see that it all, that first question, for example, it's related to stone masonry, because for brick masonry, there is always horizontal alignment. And then presence of headers, similarly, I think on the left-hand side at the bottom, you can see this presence of headers, again, related to stone masonry. If you look at the vertical section of the wall, so header is the stone that goes through the wall, which may or may not be present depending on how this wall has been built. And then alignment of vertical joints, again, whether they're offset or not, that is at the bottom right corner. So in any case, for each of these, there are 3 choices. So there is no numerical information usually needed. So it's like ranking or rating how well it fits into the ideal situation. And as I said, for this part, this method was developed, and the group of experts developed it, obviously. And so for each of these topics, they gave rating 0, 1, or 2. So the role of the participants in the project or for doing assessment is just to identify whether it is 0, which is, let's say, very, very bad, or 2, which is good, so or it is somewhere in between. And then in vertical, the first row are 3 different types of mechanisms, and those are the ones or kinematic or out of plane or in plane. So anyways, so this is what is important. So at the back end, it's already defined. So there is no choice. It's just a matter of which choice do we. And so the number of points ranges in this case from 0 to 2. And these 3 mechanisms are, first one is integration, the ones that I showed at the first slide, out of plane and in plane. So you can see that for same parameter, there are different points depending on which mechanism is also there. So it's pretty complex actually. And also they introduced masonry categories A, B, and C based on the total number of points, where category A has minimum collapse risk. So the lower is the point that is good actually for structure, and then C is the maximum. And then they classify that, again, for this particular aspect into A, B, and C, and for each mechanism as, let's say, less than 10 points and disintegration, it is category A, which means minimum collapse risk, but the higher we go for the same category, it will be different. So anyways, horizontal alignment, here they have, actually there is different rating, but similar to 0, 1, 2, but here it is letter rating R, PR, and NR, where PR, R means that there are horizontal aligned rows, could be considered as regular, I'm not sure, it's probably from some Italian word. And then PR is intermediate situations, and then R non-regular. So actually that makes sense. So And so this is quality of masonry. I said, I believe this is tuned more towards stone masonry. So in other words, if you evaluate a brick masonry building, this should not be critical for the behavior of the building. Now, the second part is actually very interesting. It's that kinematic mechanism, and it's focused on out-of-plane failure. So this is something that type of failure that has been seen in New Zealand with brick masonry. It could be seen here. It could be seen in other countries with brick masonry buildings. And it is again based on another method, which was focused only on out-of-plane mechanism. It's called SUZI-SAEE. I'm not sure how they would call it in Italy, but the title is SUZI-SAEE method. And it was developed for the Ray Lewis project, which was, I'm not sure when it was completed in the past anyways. And it had some Excel spreadsheets, which include calculations at the back end. So in that case, capacity of the structure for out-of-plane seismic actions was determined based on the virtual work principle, but based on the input data, which are given by the whoever is doing the assessment. So still, that person does not need to do the back-end calculations. And this publication is in Italian, and it gives all the details for each mechanism for the calculations. Publication is for 2007. So these are typical mechanisms, and you can see, like, if you look at the building, it's hard to imagine on this building, but let's say some other buildings in the neighborhood, we may see them, that it is possible to have a collapse of entire wall over the height if the connections are really weak. It's like typical cantilever failure, or it could be corners, or it could be top portion of the building, and so on. So anyways, these are some examples of, they illustrated, that is all from that same publication, very nicely illustrated how you can visualize that. But as you enter data, you don't really see which mechanism it is. It is a result, actually. As I said, this is from that. And the examples, and that's similar to what Jitendra mentioned, is there in New Zealand, the methodology. In fact, there are appendices, I know there, and parts of methodology that really describe how you can determine the capacity of that wall, like under which a lateral load it would, this mechanism would develop. So the kinematic mechanism would develop. And as I said, based on virtual principle, it's all transparent, very transparent for that. So, and it gives the lateral coefficient, actually, that under which it would happen. So it transfers it to something quantitative. So now, so for this, in order to come up with the mechanism, these are the 11 parameters that are to be entered, and it is the group in the category building data. That is the third category. Sorry. So just maybe let's take a few minutes to do it, and I'll show you one or two examples. Designated use, number of floors below ground. I have 5 more minutes. Irregularities in plan. Distance between the walls and so on, wall thickness, floor height. So these are now really data that you need to know. You need to find out by visiting the building. You don't need to do examination. As I said, no material testing, but some parts are there that maybe need to be estimated. So designate use, and there are explanation for each of these. So I'll show you now just some of the examples. So I circled here in red the parameters that actually require just 3 rating or ranking, and rating are 1, 2, or 3 in this value: minimum value, average value, or maximum value. So, for example, for irregularities in height, in elevation, the minimum value is 1 if building is regular, and then 3 is, for example, if 2 is when shear walls extend over the entire height, and 3, there is no significant setback in plan compared to the size of the previous floor. So anyways, these are the 3 values, and these are some examples for irregularities in plan. For example, 1 is regular building, and 3 is irregular. So we have irregularities in plan and elevation. So it is something that you can see by visiting a building and probably having a plan. So now again, for this at the back end, this is already calculated and set at the back end. For each of these mechanisms of failure, which could be these kinematic mechanisms, which are listed in the first column, ranging from simple overturning from top floor, which I showed on that diagram, there are three different, there are different values depending depending on what is the choice. Sorry. Go back. Want to progress this much. So I don't have the anything circled. So you have 1, 2, or 3 for simple overturning. All three numbers are the same. But let's say for top floor overturning, again, they're all the same. But let's say for masonry thickness, it ranges from 1 to 3 depending on which mechanism it is. So anyways, that is how it is done. And I would say that interesting mechanism, this MD3, for example, simple overturning, that is what I said, it can range from entire wall collapsing on the ground, and a very dangerous one, obviously. And you have MD4, very top wall overturning. So there are no variations of that mechanism. Entire wall from base to the top, then top floor, and then you have the third, which is vertical flexion, where the actually diaphragms are good. That is, I would say, mechanism that we could see in Serbia in the buildings that are where we have reinforced concrete floors. That is vertical flexion. That's how it is called in the methodology. And finally, the site hazard, I'm almost done. Site data. The hazard part is also input. So input is peak ground acceleration according to Eurocode 8 in order to meet this requirement. Ground type, again, according to Eurocode 8, and building exposure. And for each of these, there is explanation, so I think it's not difficult to enter that. So this hazard part is also input to the form. So the results or the output are in the bottom portion of the form. And the results are three types of results: seismic risk, which is a number. Larger number means higher risk. Index of structural response, against a smaller number means higher risk. Masonry category, A, B, and C. A is the safest and C is at the highest risk. And 4 is the most probable collapse mechanism. So those are the main outputs. And here is how risk is calculated. That is normal importance, exposure, and probability. So that is what is at the back end. So calculated by, I said, ADRISEISMIC team, and gives some number, which is then converted to index of structural response, which is inverse of index of this seismic risk. And masonry category is calculated based on that input data for based on the risk as well. And most probable collapse mechanism is one of those 6 or so mechanisms that are given there. So anyways, the idea for this rating, the numbers, doesn't make sense to us, or it doesn't resonate to Serbia, but it resonates to Italy because they use the same type of labeling as for the tax returns in Italy. So those numbers are, for them, they're really perfect. Maybe we should come up with something else here. But what is nice, I would like to say that this is the output. The output are those that you know that this building is green and is low risk, and the buildings across the street are at a higher risk. So that is the high level idea of how much at risk the buildings are, but based on some rational methodology. It's not just looking at the building and saying this is really dangerous, which is also possible. So anyways, what I want to say is, and we'll try to make them available, these reports. There are 2 reports on state-of-the-art methodology on interventions, that means on retrofitting, which I was not talking about, but that's also very nicely documented for various countries. And then methods for expeditious assessment, that is about this, and I think it's really good to know. And then 2 more protocols and guidelines for adopting it in the countries, and report on the pilot actions, that is application of this methodology in different participating countries during the project. So now we will see one example from Serbia. And I just, my role was to present the methodology. So thank you very much. It's interesting. So we'll have some time for questions after the next presentation, I hope so. So, Marko, možete da...
So I will give a short introduction, then Matija Bošković will continue. So generally, the idea of seismic risk assessment in Belgrade or Serbia raised a couple of years ago, at least in our research and working group. And then ADRISEISMIC project came in perfect timing to provide us already some tested and applied methodologies. And I was really lucky exactly at that time to have an excellent generation of students here at my courses at the University of Belgrade, Faculty of Civil Engineering, some group of 8 students, and then additionally 4 or 5, so in total 12, 30 students. So not so rare to have a really group of 12, 13 enthusiastic students that wanted to apply this methodology in the area surrounding this faculty and to collect this data that Svetlana explained, and then to see the results. That was done for the first time in Serbia or in this region that I'm aware, definitely for Serbia, for sure. And I must say a big thanks to the student that did all the, let's say, field work. And this is, let's say, the steps of the work that was done. So first, let's say we organized and collected the data, and this is the area. So maybe you can see, so here is our buildings of our faculty, and then surrounding the area. So this is mostly residential, and here are, let's say, public buildings, parks. So it was really, I think, a good example, a good, let's say, area to take, because it collects different kind of buildings by its use. And this is a nice time plan. So first, this idea of risk assessment in Belgrade, and then the meetings with the students. And I must say, I'm still not sure what attracted them, but they were really enthusiastic. So when I remember this time, it always brings a smile to my face. So they were taking the course. So it was everything voluntary. So then we divided in 5 groups. And also because we needed the documents for the state archive, there was one group always going there, communicating, which is not an easy task, and it's not always easy to get this data that was needed. And these are, let's say, divided areas for these 4 teams on the field. And they did it, yeah, we started in winter, right? So in snow and rain, and finished in spring and summer with the high temperatures, so from -10 to +40. And they did really good work, really entering, documenting every building. So it was a lot of work to do. Then Svetlana gave, of course, before we started everything, some kind of training course, explaining them in detail. Yeah, lecture, but it was, we explained them it's a training course. So they came to train, to apply this methodology. And then we had, of course, several progress meetings. And here are some photos from the site. So they were taught to recognize the type, the structural type, of course, to document the number of floors. Also, they communicated with the people living there to get, the data. Sometimes they entered the basements, the roofs. So it was quite a lot of work. And then when we collected all the data, it was needed to organize it and processes. You can tell me when I should start. And Matija did, Matija, sorry, did most of the work afterwards to really combine all these information about 468 buildings, something like that. So almost 500 buildings, everyone documented with all this data in the Excel sheet. And then he, with support of a couple of students, but mostly he had to visit some again when he started filling the forms, because some data was missing. So really a lot of work. And then he applied the methodology, let's say, sucked in all the data that we collected, and then he made the results of the methodology. Now, the floor is yours, right? Yeah. Okay. So thank you. I was just, let's say, lucky to be on the organizational part, and Matija was leading, let's say, the application part.
Thank you, Marko, for such an excellent introduction. And in the following section, called the building portfolio, I will present some interesting facts about the buildings which were presented before. We made a comprehensive statistical classification of all buildings in the considered neighborhood, and according to their various parameters they could have. Some of them were year of construction, type of structural system, presence of extensions and irregularities, and I'm going to explain some of them. If we consider the year of construction of all considered masonry buildings, we can observe that the most of them were built between the two world wars. Since 70s, their construction has decreased significantly, probably due to increased construction of concrete structures in that period in our country. Observing the structural system of all considered masonry structures, we can notice that more than a half of buildings were built as unreinforced masonry walls, unreinforced masonry buildings with flexible diaphragms. On the other hand, more than 40% of buildings have some form of extension, while 3/4 of observed buildings have some irregularities either in plan or in the elevation. And now I'm going to show you an example of a masonry building from considered neighborhood and collected ADRISEISMIC methodology for. As an example of masonry building, we have a building in Hadžiđerina Street, number 527, and that building was considered in detail, such as other buildings. First, basic data about building was filled out, followed by construction parameters of building. After that, the masonry quality section was completed. Considering that standard solid brick of rectangular shape and cement mortar were used at the time of building's construction, the best categories for masonry quality were assigned. Giving in mind that this building is regular both in plan and elevation, and that is an unreinforced masonry building with thick walls and regular floor height, these parameters from building characteristics sections were assigned. After choosing particular parameters for site of our building, we obtain the result. The result is given in 4 types: an index of structural response, masonry category, most probable collapse mechanism, and seismic risk category. As you can see, for this building, ADRISEISMIC methodology assesses that that building is at a low risk. And now let's move on to the results of application of ADRISEISMIC methodology. We completed the ADRISEISMIC methodology form for all considered buildings in the neighborhood, and we obtained the result. I'm going to show you the result in the form of percentage of all considered buildings belonging to specific seismic risk category, as we believe that the seismic risk category is the most important part of result. As you can see, this methodology assesses that almost all buildings belong to low seismic risk, category. It is believed that this result is not entirely expected and correct. Hence, we conducted a tiny modification of original methodology. And let's move on to the modification of methodology. The ADRISEISMIC methodology was developed for Italian construction practices and regulation, thus requiring certain adjustments for Serbian context. The modifications were achieved through calibration of specific coefficients related to input of horizontal ground acceleration, transversal wall distance, floors above ground, wall thickness, and expected utility on seismic risk of particular building. Additionally, we implemented a brand new parameter for building extensions. It is crucial to implement that parameter as there are so many buildings in Serbia which have extensions. Again, we completed all forms of ADRISEISMIC methodology for all considered buildings, and we again obtained the new result. As you can see, now we have more than 60% of buildings to be at medium risk. This figure shows the considered masonry buildings of considered neighborhood, colored according to the belonging seismic risk category assessed by ADRISEISMIC methodology. And here are the results, compared results of original ADRISEISMIC methodology and modified ADRISEISMIc methodology. Finally, I want to present a comparison between this methodology, this ADRISEISMIC methodology, and two other methodologies. We choose two different methodologies that have such different concepts and type of outcomes than ADRISEISMIC. We used FEMA P154 and ISIS methodologies. FEMA and ISIS methodologies assesses the seismic risk through final number of points for a particular building by assuming specific coefficients for specific category. You obtain final number of score. On the other hand, ADRISEISMIC methodology gave seismic risk category as a result. It was very difficult to make comparison between these methodologies because their concepts and type of outcomes were very different. But we made a simple approach by transferring points of FEMA and ISIS to seismic risk categories of ADRISEISMIC, and we obtained this result. As I stated earlier, original ADRISEISMIC methodology assesses that almost all buildings belong to low seismic risk category. On the other hand, results of modified ADRISEISMIC methodology are believed to be more appropriate. ISIS and FEMA gave more conservative results and assesses that more than 60% of considered masonry buildings were at high risk. Quite different results. We want to conclude that original ADRISEISMIC methodology is a very good starting point for seismic risk assessment of buildings in urban areas in Serbia, but it needs to be modified to fully correspond to Serbian construction practices and technical regulations. On the other hand, FEMA and ISIS predict that more buildings should be given a bigger attention and a detailed assessment for such buildings should be conducted. Thank you very much for your attention. Thank you.
Thank you very much, Matija. And thanks to all presenters for keeping on in time exactly. I mean, I think 1 minute difference. Amazing. So now we have some time, another 15 minutes for questions for all presenters, since all presenters were just presenting, there were no question period after. So starting with Jitendra Bothara's presentation and then all the others from this. So do we have any questions from here in the room and also from online presenters? I understand there is some chat and maybe Matija can help. That is no questions. Okay, in the chat, just comment. So any questions for Jitendra to start with? And since he's your guest, we must ask him difficult question that is Serbian custom. Very difficult, yeah. And this is examination room, you know, so we all had exams here, so if you don't know, it's difficult.
So maybe there are some confusion.
Do you want to come and
Yes.
so because online participants cannot hear you, that's the only thing.
So maybe a comment on maybe there was confusion. We also have a preliminary assessment methodology, and we start from preliminary or initial, we call it IEP methodology. We start from IEP methodology to assess building. And then if we find it is less than 34% of new building standard or current seismic code, then it goes to detailed seismic assessment. So that's a typical process we follow, because everything in New Zealand is tied to what is the percentage capacity of the building, because that's tied to the building act. So rather than looking at the risk, we look at what is the percentage capacity in terms of new building or the seismic code. But it starts from preliminary, and preliminary or initial seismic assessment is generally done by city council. And if it's less than 34%, then notify the building owner that your building is less than 34%. Your building is earthquake prone, what you want to do. And now it is the building owner's responsibility to prove it's a more than 34%. If they don't want to do anything, and if it is not, then they have to either fix the building, make it above 34%, or remove the building. So I just wanted to make it.
Thank you, Jitendra. Is that preliminary, the approach or the methodology, is it also part of the same package as the one that we discussed? So it is on the same link, so we will make that accessible to colleagues.
If you look at these guidelines I talked about, the set of, I think, 13 guidelines. So one of the guidelines is on initial seismic assessment. And there are two methodologies. One is generic methodology, and one is unreinforced masonry methodology. But it's still, our methodology is a qualitative, much less quantitative than you presented, but more it is on the gut feel. If you feel comfortable standing in front of building, looks a good building, okay, move on. Of course, we have to do some numbers. There are some methodology. We have to follow the protocol. At a glance, if you feel, nah, this building has somewhere problem, then of course, then you start thinking differently. So that's how we work.
Thank you. Thank you very much.
Yes.
Can you maybe come here, Jitendra, and repeat the question? Repeat the question. So
If I understood right, your question was, what was the thickness of the walls that typically collapsed? Most of the walls, the buildings, those are constructed pre-1931. After that, there are no unreinforced masonry buildings constructed in New Zealand because of the law, and a lot of people died in unreinforced masonry buildings in 1931 earthquake. So most buildings are pre-1931, and typical wall thickness was 350. When I say 350, because our brick size is 240 millimeter long, 110, and could be 50 millimeter to 70 millimeter thick. So typically 350, but there could be 230 or 240 thick walls also. So it depends on, if it's a 3-story building, let's say this way, if it's a 3-story building, top story will be 230, 240, then half brick more. So become 350, and ground floor is either 350 or 460. So each story is a half brick type of thing. That's a
Okay.
typical room.
Thank you. And the question.
Yeah,
from Marko.
please, Marko.
Marko, maybe come.
Yes.
and,
One
ask
short
us.
question,
difficult
regarding this 34%. If we
Yeah.
talk about the risk, so one is seismic assessment, but seismic risk assessment. So is this 34% the same for house for one family or for public building? Because this for
Yeah,
the
yeah,
main
you should. Yes.
all the risk
Yes,
methodologies
yeah.
take this into account.
Yes, agree. Thank you. Thank you for asking the interesting question. Because most of the people in New Zealand live in one-story timber houses. And as I mentioned, we all live in one-story timber houses. Apartment buildings are mostly in urban areas, not in rural areas or even in suburban. People live in small one-story timber houses. Timber houses are very resilient because they are very light, and even the injury, probability of injury is very low. So the law doesn't require these buildings to be assessed. But if the building is, or even timber building is 2 or more than 2-story high, and it has more than 2 household units, then of course people are now something like 10, 12 people, so risk is higher. So that has to be assessed. So most of the time what we find is, if it's a residential one-story house, we don't have to assess. But if it's a one-story timber house, but it's a commercial, being used for commercial, then it has to be assessed. But usually timber houses would pass the test, easily pass the test, 34%, unless these are on the sloping ground with long piles or something. But masonry buildings will typically fail 34% test. And that means it has to go through the detailed seismic assessment. But we don't look into terms of risk. We always look into terms of what is the percentage of seismic mode, what percentage is admit, because it's, and that percentage, 34% is, we say it is a moderate level earthquake.
Because the aim of this methodology is to prioritize.
Yeah.
So to say, okay, these red ones, check them first,
Yeah.
in this
Yeah.
detailed seismic assessment, and then if it's lower, then.
Yeah,
there are
but so your
34%.
methodology and our approach is very different in the sense because you are prioritizing a big group of buildings, whereas we are not prioritizing. We are saying this is a house owner's or the building owner's responsibility. He has to fix this building in next 15 years if it's less than 34%. Usually people go for above 65% because of the commercial pressure. Because if you only do 34%, or if it's a 40% building, the real estate value of that building is low. So if they go to 70%, they get much higher return when they sell the building. So that's a,
Sorry,
yeah.
this, when is this check for 34% done? So when you want to sell it, or
No.
the state says everyone has to check it from now on in the next 1 year, or
No.
how does it work?
Okay, thank you. So what happens is the preliminary assessment is typically generally done by the city council or municipal council. So it is done by municipal council. So they hire engineers because it is tied with liability, professional liability. So it is done by consultants. And then if the building is less than 34%, then it is the responsibility of city council, because it is implemented by city council. It is their responsibility to notify the building owner that your building is less than 34%. If it is more than 34%, they don't have to notify. So now it becomes building owner's responsibility because their building is less than 34%. They have to prove it is above 34%, or they have to fix the building. So it is basically city council transfers that responsibility to the house owner. That's how it works in legal sense. And so basically this started in 2006. So at the moment, a lot of buildings, because they got to that maturity of 15 years, so a lot of buildings are under strengthening around the country. And it applies to all buildings, including government buildings and private buildings and council buildings. It is not only the private people. Because in New Zealand, government is a person. So the same law applies to the government also, or the councils. So there, it is becoming an issue for councils because they have a lot of buildings and their buildings are earthquake prone. So they have to fix the building. So that's how it works in New Zealand context.
Thank you very much, Jitendra. Do you have any questions for other participants? You can ask the other participants anytime. We are local, but still, if you have any questions or comments, please go ahead. And anybody from online, we know that there are 14 participants, including I think ourselves, but if there are any questions from online, you can unmute yourself and ask question if you want. There's no need to write in chat. Please feel free to, for any of the participants, if you wish. No, it seems that none of the, anyways, you can contact us also anytime. Marko, no questions for now. No, everything was okay. So then in that case, yeah, we are 3 minutes to the end. We have all of us have some other events today, so we need to complete this session. Thank you very much for participating. We had 20 participants online as well, so thank you. It was very interesting. And first of all, thank you to Jitendra for coming.
Thank you for inviting. It was amazing experience for me to come to Serbia. Learn a lot of things. I think I give less than what I got here. I learned a lot of new things. Thank you. Thank you.
Thank you. Thank you. Great.
So,